My name is Evgenii, and I'm going to tell you about non-Gaussian tensor programs. First, recall the two main limit theorems in probability theory. The first is the law of large numbers, and the second is the central limit theorem. Both state that an average or a scaled average of a sum of ID random variable converges to something that doesn't really depend on their distribution. It depends only on several first moments. And this property we shall call universality. Can I formulate a similar universality principle but for neural networks? The possible conjecture will be that as the width tends to infinity, two different ID random initializations of a neural network induce identical training behavior as long as they sample weights with the same mean and variance. In some cases, we can indeed validate this principle. For example, if we take a matrix-shaped vector weight tensor W of size n by n, and we swap all the weights which were Gaussian to their non-Gaussian counterparts, we will get the same output of the network in the limit of large widths, simply by applying a central limit theorem type argument. However, in some cases, this principle fails. For example, if among our weight tensors there is a vector u of size n, and we swap its weights with its non-Gaussian counterparts, then the output of the network in the limit of large widths can be alternated. And there is an example here. So the universality fails for vector-shaped weights. Similarly, we can show that for scalar-shaped weights, this also fails. And it makes us think that, okay, the universality may hold, but only for matrix-shaped weights, but not for scalar-shaped or vector-shaped weights. So we have to sample matrix-shaped weights. We could sample it from a non-Gaussian distribution with the same mean and variance, but for scalar and vector-shaped weights, we have to sample them the same way. However, this conjecture is obviously false, simply because any vector can be thought as a matrix, simply because of that. However, it is nearly true, and precisely we will call a parameter tensor scalar-like if its size remains constant as width becomes large. If there is only one dimension of this parameter tensor that becomes large, as width becomes large, then it is vector-like. Similarly, if there are two dimensions, then it is matrix-like. And the universality, in fact, holds for if we swap matrix-like weights with the same, we sample them from a different distribution, but with the same mean and variance. And that is the correct universality principle. In fact, this principle is a corollary of a more general universality principle for tensor programs that I'm going to introduce soon. Suppose we are given L matrices of size n by n, M0 vectors of size n, and M0 scalars. Then a tensor program is the following iteration. On each step I, we generate a new vector x by applying a nonlinearity element-wise to all of the previously generated vectors and scalars. Then we generate a new scalar by averaging the entries of this vector, and we generate a new vector by multiplying this vector by a matrix. Why we are interested in tensor programs? Simply because they are very expressive. They can express a forward path of a neural network of any architecture, similarly as a backward path, and as well any number of gradient descent steps. That is, if we have a network with k outputs, then for each gradient descent step t and any input psi, the network output after t gradient descent steps can be expressed as a set of k scalars in certain tensor program. That's why if we're interested in identical training behavior, we're interested in the limit behavior of the scalars generated by a tensor program. So the conjecture for universality would be that if we that any scalar generated by a tensor program converges, and its limit does not depend on mean and depends only on mean and variance of the distribution of matrix entries. So there are two, in fact, there are two statements here. The first, that scalars converge, and the second, that the limit doesn't depend on the distribution of weights. The first statement is given by the called master theorem. We shall call it Gaussian master theorem. It tells you that if all initial vectors are sampled from ID Gaussians, all matrices have ID Gaussian entries and certain technical conditions and linearities, then any scalar generated by a tensor program converges almost surely to a certain deterministic limit that we can compute. And our main result is a non-Gaussian master theorem where we have relaxed the assumption of Gaussianity of matrix entries. So they could be non-Gaussian. And in this case, all of the scalars converge to the same limit. And that's our main result, and it gives universality this way. And also, the original Gaussian master theorem had a lot of applications. They're listed on this slide. For all of these applications, we have to assume that the relevant matrices, relevant weights were Gaussian. And since armed with our non-Gaussian matrix theorem, we could get exactly the same applications, but without this assumption. Thank you for your attention.